Okay, we're going to work on the Archimedes problems 21 through 25. And in these problems, the equation we're usually using is density times volume. Density times volume now gives us our mass. And if we take that times gravity, that'll give us a weight. So we can either figure out a downwards weight of some object, or if we take the density of the liquid or something that the object's in place of this density, then we would be figuring out also a weight, but it would be a weight as a force, and we'd be calling that an upward buoyant force. So we could use this to calculate a downwards weight or an upwards buoyant force if we use this as the density of the object, or we use this as the density of the stuff being displaced by the object. That's kind of what we're doing. So in 21, we have the density of ice is 917, the density of seawater is 1,025, and an iceberg has a volume of 5.2 cubic meters. What is the weight of the heaviest polar bear that the iceberg cannot support without sinking completely beneath the water? So the first thing we can do is we can use this equation to figure out what is the weight of the ice cube, or the iceberg, and that would be 917 times the volume, which is 5.2, because 917 is the density of ice, times the volume, times 9.81, and whatever that is, that would be our downwards force. And then we can figure out the buoyant force, which would be the weight of the water being displaced. So that would be taking 1,025, the water, times the same volume, 5.2, times 9.81, and that would be our upwards force, buoyant force. And right now, the buoyant force would be a lot bigger than that, so we'd subtract this downwards force from the buoyant force and see how many newtons we have. And however many newtons we have, that would be the weight of the polar bear that we could put on here, so that the polar bear's weight and this weight of the iceberg would then equal the buoyant force. So hopefully that made sense. Let's look at problem 22. A duck is floating on a lake with 25% of its volume. Here's the duck. Pretty sad. 25% of its volume is underneath the water. This is something that's really nice to know, because if you take 25% of the fluid that you're floating in, so 0.25 times 1,000, you will have the density of the object. The density of an object is the percent that's floating underneath the water times the density of the water. That's why, like, an iceberg is dangerous, because, you know, like 90% or so of the iceberg is underneath the water. Well, if the water density is 1,000, that means the density of ice is around 900, and we know that that's the case. So whatever percentage of an object is underwater, take that percentage times 1,000, and you'll have your density of the object. Okay, number 23. An object is solid throughout. When the object is completely submerged in ethyl alcohol, which has a density of 806, its apparent weight is 15.2. Okay, we know it's not its real weight, so we're going to take weight minus the density of its buoyant force. So the weight minus its real weight minus the density of ethyl alcohol times the volume of the object, which we do not know. We don't know the actual weight either. And that will equal, or times gravity, and then that will equal, it says, an apparent weight of 15.2. Okay, so then what if we completely submerge it in water? Well, we get its real weight, and these two weights are equal, of course, minus the density of water, which would be 1,000, times the volume, which we don't know, times gravity, equals 13.7. So what we could do here is we'll take this equation here, and we'll solve it for like the weight. So the weight would equal 15.2 plus, let's go ahead and put the density in. What was it? It was 806 times volume times 9.81. And this equation here, the weight, would equal 13.7 plus 1,000, this is in water, times volume, times 9.81. And we're trying to solve for the volume of this object. Well, we know the weights of the object are equal, so we could set this equation equal to this equation and then solve for V. Hopefully that'll help you solve the rest of it. Okay, number 24. By the way, in that last problem, your volume was supposed to eventually be converted to milliliters, so don't forget about that. 24, what is the smallest number of whole logs that can be used to build a raft that will carry 4 people if they each have a mass of 80 kilograms? Okay, so the first thing we can do is figure out what is the mass of a log, and that's the density times the volume times gravity. That's, well, I guess this would be the weight, technically. Yeah, so let's just do the mass. We just worry about the mass. So the density of the log, 725, excuse me, 725 times the volume of a log would be a cylinder, so it'd be pi r squared times height. And your radius and your length were given, or height is your length here in this case. So you'd figure out the mass of a log. And you could also figure out, if we took that times gravity, you'd be finding the weight of the log, if that helps. Now we can figure out what's the buoyant force of a log. Well, that'd be 1,000, the density of water, how much water is being displaced, times pi r squared times height, and times gravity again. That would be our buoyant force. This is our weight. This is our buoyant force. And that's why I didn't really want to do the gravities, because I could cancel out the gravities. Instead of these being weights, they would be kilograms. And I could subtract them and see how much, subtract them and see how much weight I could be using. And take 4 times 80, that's 320, and I could take the 320 and see if I subtract these, I would have, I think if I subtract it, I think I get like 16.6 or something kilograms that each log could support. This is a single log here. So each log could support 16.6 kilograms. If I have 320 kilograms divided by 16.6, I'll be able to figure out how many logs I could use. Okay, and then finally 25. We have an 81 kilogram person floating in water due to a life jacket. The jacket has a volume of 3.1 times 10 to the minus 2 cubic meters, completely submerged under the water. The volume of the person's body that is underwater is 6.2 times 10 to the minus 2 cubic meters. What is the density of the life jacket? Okay. Well, the downward force or mass of the whole thing would be 81 plus the mass of the jacket. We're going to have JB jacket. So that would be your downwards force. Okay, what would be your upwards force? Well, it would be the volume. It would be the density of water, 1,000, times the total volume. And we can figure that out because both volumes were given. The volume of the person under the volume of the person's body that's under the water and the entire volume of the life jacket was given. So we could add those together and get the total volume. And we do it times gravity again, but we don't need to because we're going to balance that out. So this would be the total downward kilograms downwards, and this would be the total kilograms or buoyant force upwards. And we'd have this total volume here. So we could actually set these to be equal, and then we'd be able to solve for the mass of the jacket. Once you know the mass of the jacket, we are already given the volume of the jacket. You divide the mass of the jacket by the volume of the jacket, and you're going to have the density of the jacket. So it'd be pretty easy to do. Okay, let's see. Is that all the problems? That was problem 25. Okay, so that hopefully will help you on that set.